Welcome back. In this video, we're going to address the most complicated fatigue or dynamic loading scenario, which is when we have combined different types of loading. So let's imagine a part that has some geometry, and we'll go ahead and use a similar part to the example we had before, where there's some fillet and maybe even a hole, right? So we have some stress concentration factors. Now we looked at this problem as putting it under tension, and that tension, we'll call this load F, would have some cycles between maximum and minimum. We could also put this part under bending and put it under some bending moment. And that bending moment might have a different fluctuating stress. Finally, we could put this part under torsion and have shear stress due to torsion that also fluctuates at an entirely different time scale. So let's look at all of these together. Our force, and thus the stress that's due to that force, may fluctuate. Let's consider it fully reversed. At the same time, our bending moment may be much faster. And at the same time, we could consider our torque to basically be turned on anytime we're using the part. And so it may only have one value. And all of these things can be different. This is just a hypothetical example. So what do we mean then when we say, will it last 10 to the 6 cycles? Well, are we talking about axial cycles? Are we talking about bending cycles? Or are we talking about torsion cycles? For one part experiencing combined loading, we have to be able to figure out a way to determine the cumulative effect of all of those loading stresses together. So a good way to do that turns out to be von Mises stress. So recall that we had von Mises stress where we had sigma x squared plus sigma xy minus sigma y squared plus 3 tau xy. This allowed us, and all of that to the 1/2. This allowed us to evaluate different stress combinations. We could have bending in the x direction, we could have axial stresses in the y or the x direction. We could have shear due to a number of things, but it allows us to put them all together into one single stress value. So basically we're going to do the exact same approach now for fatigue. And we have to be careful about looking at a particular time scale. So for us, we'd probably want to look at the one that's causing the most amount of damage. So within a particular cycle, say one cycle of the bending loading, what is the minimum and maximum for each of these? So in this situation, our torque mean and maximum are the same thing. This is effectively static loading at that time scale. For the bending cycles, the axial load basically looks like a constant load. And then for the mean bending stress, we have one cycle. So in general, we'll take the smallest cycle we can and evaluate the loading over that. So what we'll do is we'll come up with a new formulation for our mean and amplitude stress values, which is our modified mean and amplitude. So altogether, these look like this. We will look at the stress concentration factor, Kf, considering bending, and multiply that times the amplitude stress, which is due to bending. We will also want to add to that the Kf, any fatigue stress concentration factors we have for axial loading, times the amplitude in the axial loading area. And in this situation, we're going to divide by 0.85. That comes in from the fact that when we choose Marin factors, we have to choose a particular type of loading. So when we are doing Marin factors, recall Kc is the loading factor. So which Kc would you choose in this situation when you have all three types of loading? Well, you have to choose one, so we'll choose bending. And to modify for that choice of bending, we have to divide by that 0.85 that we would have gotten if we had said it was in axial loading. We are not going to include anything for the torsion part because that actually gets accounted for already. That's what that 3 in front of the shear stress is from. So the square root of 3 is where that number comes from. So let's include that part. 3 times Kf Kfs that we get from torsion. And we're going to multiply that times the amplitude stress squared. Times the amplitude stress. So the squares on this are here, and all of those values then to the 1/2. So that's the von Mises form. We can also do the same thing for our mean stress, but it will look a little bit different. We will have our Kf for bending times our sigma mean for bending plus the Kf for axial times our sigma mean for axial. And we do not need to include the 0.85 here. The reason is, again, for static loading, we don't have any fatigue contribution. So for the static loading, we're not going to include the Marin factors because they don't play any part in comparing the mean stress to the ultimate strength. We compare the amplitude strength to the endurance strength, and the endurance strength is where we used that 0.85 Marin factor. Hopefully that's clear enough. And then we'll have that same Kfs applied to the mean shear stress, but the 3 squared. And all of that, again, to the 1/2. So those are the von Mises forms. And again, in similar situations to what we talked about before, when we were looking at our stress to cycles, and we plotted something like this, and we're comparing it to how close are we to this line, to this point, NF equal to 1, which means 10 to the 6 cycles. This all assumed fully reversed loading. Fully reversed simple loading, to be specific. So now we are in the situation where we don't have fully reversed and it's not simple. So what we need to do, if we want to figure out the number of cycles this thing is going to last, is we need to come up with basically what is the equivalent stress. So the equivalent stress to a fully reversed, we'll call this the equivalent fully reversed, is equal to sigma A m over 1 minus sigma m over SUT. And then this is those primes. So that's where those come from. Now, again, just like we were talking about in the last video, if sigma m prime is less than 0, then it tends to not lead to crack formation. It's compression, so no cracks. So if that's the case, then you can consider the 0 and the effective reverse stress is the same thing as the amplitude, or this von Mises form of the combined loading amplitude. So that's it. That's fairly simple for the simple modifications. overall the process is still going to be the same. So the fatigue process for combined loading looks basically the same. First of all, we'll start with material properties. Then we can modify the endurance strength, the hypothetical endurance strength, to an actual endurance strength using the Marin factors. And here is where we need to assume we are in bending. So Kc equals 1. And we fix that assumption in the von Mises form. Next part is calculating any stress concentrations, if they exist, calculating stress concentration factors, and we'll have to do this per loading. So we'll have, like I said, a Kf for axial. We'll have a Kf for bending. And we'll have a Kfs for torsion. That is a shear stress concentration factor. So the only difference is now we'll have to calculate 3 for each point when we're under all 3 types of loading. The fifth step here is to figure out mean and amplitude stresses per loading. So the mean and amplitude stresses are based on the minimum and maximum. So we'd have sigma max due to bending, sigma min due to bending. Perhaps if we're in direct axial, we'll have some sigma max and sigma min due to the axial portion, and we'll have some shear min and shear max due to the torsion portion. We need to apply those concentration factors per each one, and we can do that within the mean stress calculation. So apply our Kf or Kfs's and calculate the sigma mean von Mises form and the sigma A equivalent or von Mises form. So that's following this formulation above, where we have Kf times the bending plus the axial. So combine the bending stress and the axial stress, since those are both, as long as they're in the same direction. So this is making an assumption that they're in the same direction. So if you've got bending in 2 directions, you'll also have to basically expand this to include those. So this assumes obviously the axial stress needs to be in the same direction as the bending stress. If not, then you have a sigma y component, say from one of the others, and you need to include that, and you do it in the same exact way in the von Mises approach. Your Kfs might be a little bit different because the notches may not be in the same direction, or they may not be there at all. Okay, so you calculate the sigma A and sigma mean, and from there we can just use those in our Goodman equation. So basically, or the ASME elliptic or Gerber, whichever one you wanted to use, but basically check for fatigue failure. And again, we have 1 over NF equals sigma A prime over our modified endurance strength, sigma M prime over the ultimate strength. And if our mean stress is 0, our fully accounted modified mean stress is 0, we can just look at the amplitude side of that and make our assumption off that. If NF is less than 1, we are not predicting infinite life, but we are predicting some life. We can figure out an equivalent fully reversed stress based on the sigma A over 1 minus sigma M over SUT, and use that to figure out how many cycles something will last. We looked at this equation before, but you have, of course, the fully reversed stress over A all that will 1 over b. And the values for a and b are calculated the exact same way as they were before. Finally, we need to check for yielding because it's possible that we are above the fatigue line there, but we have actually surpassed our yield point, so it won't do any number of cycles beyond the 1 because it will simply break. Now, here we could go back and look at the maximums for each one and combine them and use von Mises, and that's fine, and we'll get you the most accurate answer, but the quickest answer is just looking at the yield strength compared to what I might call the modified maximum. So that is the yield strength, and we can do basically sigma A plus sigma M. So that's basically a modified maximum. And note, this includes stress concentration factors. And when we did yield stress, we said don't use stress concentration factors. Well, it increases the value of the stress higher than it really is. And so the problem here is that you're underestimating the strength of your part. You're overestimating the stress. And so the way that this is wrong is conservative. So if your sigma A plus sigma M is still less than the yield strength, even when you include the stress concentration factors, then yes, it will not yield. You take the stress concentration factors off and you use them more accurate but more time-intensive way, and you'll also find that that value is even more so not going to yield. So here, again, for most practical purposes, we don't care what the yield strength is. We just care that it's actually not going to break. So that's the process for applying the combined fatigue failure loading. In following videos, we'll basically just do an example of this and you'll see how it's applied. Until next time.